Welcome to Pre-Calculus Sequences and Series. This video is going to be an introduction to what the heck is a series. Well, if you happen to Google it or look it up in a dictionary, you will find maybe several things. Or maybe you've heard the word series used several places in your lives. A television, a series is a set of episodes. So we say, oh, I'm going to watch this series, right? Or what series are you watching, right? It's just a set of episodes. In baseball is a series, a set of games played. So the World Series, for example, is a set of games, and you play until somebody wins 4. In retail, a series is a set of products under a common name, like the Lauren Conrad collection or the Beyonce collection or whatever. It's a set of products, clothes, moisturizers, I don't know, whatever, that are sold under a common name. Even in currency, so money, right? A series is a set of bills printed at the same time. So if you actually look at a dollar bill or a $5 bill or a $20 bill, you could see what series it is. And that series is just, the set of bills and that were printed all at the same time. So that was that series. So anyway, in mathematics, a series is very different, but kind of similar at the same time. So in mathematics, a series is simply a set of numbers. Just like on television, it's a set of episodes. Baseball, it's a set of games. Retail, it's a set of products. It's a series is a set of numbers in mathematics from a sequence, right? So we know a sequence is a list of numbers. So a series is a set of those numbers. But what's very different is that a series in mathematics is adding those numbers together. So a series is not just looking at a set of numbers or just having a set of numbers, but it's taking that set of numbers and adding them all together or summing them, and sum means add, of course. So let's take a look at a couple of examples. Here's what a couple series look like. Now, again, honestly, a series is just a sequence with plus signs. So here's an arithmetic sequence that is actually turned into an arithmetic series. So we have the sequence 5, 7, 9, 11, 13, 15, up to. So that's arithmetic. But again, we're instead of just looking at them, which is a sequence, we're going to add all of them together. So we're adding those together. So there is a set of numbers from an arithmetic sequence that we're going to add together, and that is a series. A geometric series looks like this: 3 plus 6 plus 12 plus 24 plus 48. So this is times 2 times 2 times 2 times 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24, and so forth. So this is geometrics. We're multiplying by a common ratio there too. But again, I'm not just looking at the numbers anymore, which is a sequence. I'm going to add them together. So here's a set of numbers that came from a sequence, and I'm going to add them together. That is a series. And we have that other category. So this would be it's not arithmetic nor geometric, but it's another sequence: 1, 4, 9, 16, 25, 36, 49. In fact, that's a very easy sequence. It's just n squared. But anyway, instead of just looking at the sequence, we're going to add the terms together. So we have a set of numbers from a sequence, and we're going to add them together. So that is a series. So what's a series? It's a set of numbers from a sequence that we're going to add or sum together. Now, of course, we could just grab a calculator and add these together, but let's find a different way to represent a series. Again, these are 3 examples of a series, right? Adding numbers together, right? Adding numbers from a sequence together. But there is a kind of a cooler, more mathematical way that we represent a series, and that is with what's called summation or sigma notation. So once again, a series is just a sum of terms from a sequence. And to describe the sum of terms, we could certainly do what I just did in the previous 3 examples, just show adding them together. But this is, again, just a more mathematical way. And I want to explain before I dive into this notation is why it's needed. Because if we just go back to these examples, this first example, arithmetic, it had 6 terms. Well, it's not very difficult to write 6 terms: 5, 7, 9, 11, 13, 15, very easy. But imagine if you had 100 terms or 1,000 terms that you wanted to sum together. You would certainly want to write all of them out. So sigma or summation notation is a more condensed way to express a series. So first off, it uses the capital Greek letter sigma. And that capital Greek letter sigma is that. So that's why it's called sigma notation. But sigma is the mathematical symbol for the sum or the summation, add together. So when we see this sigma, what we're doing is we're saying, hey, we're going to add a bunch of numbers together, and that's called a series. That's why this is a way to represent a series. Now, underneath the sigma, you will see the lower limit. This is the term that we start with. Now, we don't have to start with 1. We could start with 2, 3. We could start with any term we want, but the bottom number tells you what term to start with. And the top number up here is the upper limit, and that tells you the term to end with. And that's pretty much tells you what's the first term and what's the last term. And then right here, this is the formula to find those terms for you. Okay? So once again, bottom number is what tells you to start. Top number is with the term you're going to stop with. And then next to the sigma is the formula that gets you those terms. So again, in this particular generic format, we're going to start with the first term. So that's the 1 right here. So the first term, and we're going to keep adding, and we're going to keep adding until we get to the nth term, which is again whatever term they tell us to stop with. So let's look at a couple examples to make sure that this is so easy. Now, before we look at examples, I want to make note that it doesn't matter what variable you use. Right? Just like in functions, right? We typically use x, but you could really use any variable that you want. So again, I have I written here, but again, you could use n, k, w, m. It doesn't really matter. All right, so let's actually go back to these problems real quick, and let's express these as summations. All right, so first, I'm going to go ahead and use my sigma for summation. Now, I clearly started with the first term. So I'm going to say, let's start with the first term. And I added the first term, second term, third term, fourth term, fifth term, sixth term. So I'm going to put a 6 on top because that means I'm going to stop after the sixth term. And the next thing I need is a formula. I need a formula that goes next to this. Well, that's easy because we learned how to write an arithmetic formula. So again, the first term is 5, and the common difference is 2. So my formula for any term is going to be the first term plus 2 times n minus 1. I'm going to go ahead and distribute that 2 to get 2n minus 2. So my formula would be 2n plus 3. 2n plus 3. And that is what goes right here. So this notation is the exact same as this notation. So this is just actually writing out the series, where this is just a notation that represents that series. So it tells us that we're going to add the first through the sixth term, and this is the formula to generate those terms for me. So again, plug in 1, you get 5. Plug in 2, you get 7. Plug in 3, you get 9. Plug in 4, you get 11. Plug in 5, you get 13. Plug in 6, you get 15. So I'm getting messy over there. And there's your series. Again, pretty easy. And then you can grab a calculator and add them together. All right, let's do this next one that is geometric. So once again, I'm going to grab my sigma notation here. I'm going to start with the first, and let me use a different letter. I just want to make sure that you realize you don't need to use I. You could use anything you want. My first name is Mike, so I'm going to use an M for Mike. It doesn't matter, right? So M equals 1, start the first term, and then I go into 1, 2, 3, 4, 5. Looks like I'm going to add the first 5 terms, so 1 through 5. Now, I need a formula to generate these terms for me. So again, this is geometric, so we know that the first term is 3, and the common ratio is multiplying by 2. So my formula is 3 times 2 to the m minus 1. There you go. So again, this is telling me to plug in 1 to get the first term, 3. Plug in 2 to get the second term, 6. Plug in 3 to get the third term, 12. Plug in 4 to get the fourth term, 24. Plug in 5 to get the fifth term, 48. And I'm going to stop there because I was told to stop at 5. And go and add them together, you get your series. All right, this last example is the other category, which can be, again, a little trickier because there's no formula. We just have to kind of see it, but I chose an easy one here. So once again, I'm adding first, second, third, fourth, fifth, sixth, seventh term. So I'm going to add the first 7 terms, starting with 1. And the formula there, again, I hope you see it, is just n squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, so forth. So this summation notation is equivalent to this series. All right, let's look at some examples going the other way. So here's some examples that start with the sigma or summation notation, and we want to write out the series. So once again, it's so easy, right? The bottom number tells you the term to start with. So I'm going to start with the first term, and I'm going to add all the way through the fifth term. So the first term is found by plugging in 1. 3 times 1 is 3. The second term, 3 times 2 is 6. The third term, 3 times 3 is 9. The fourth term, 3 times 4 is 12. And the fifth term, 3 times 5 is 15. So there is my series. Now, again, I'm not going to waste my time showing you this because I know you guys know how to go to a calculator and add numbers together to get the final answer. You could do that. What I'm trying to do is show you sigma notation versus series, the addition of several terms. All right, let's do this next one here. Now, this time, something weird happens, right? We're going to start on the fifth term. Again, you could start anywhere you want. We typically may start at 1, but you can start with any term you want. So this wants me to start with the fifth term and then go to the eighth term. So the fifth term would be 1 plus 25, 26. The sixth term, 1 plus 36, 37. The seventh term, 1 plus 49 is 50. And the eighth term, 1 plus 64 is 65. So there's the fifth term, sixth term, seventh term, eighth term. And that's 5 through 8. And I'm going to add them together. You guys can do that on your own. It's pretty easy. And you get the series. I mean, how easy is this? This is pretty cool, right? All right, so here's another one. I chose this one for several reasons. One, it involves some trig. I don't want you to panic. It's actually quite easy trig. And I also chose this one to show you that, hey, this time I'm starting at 0. Now, when you talk about sequences, there is no such thing as a 0th term. But when you're doing a series, if it says to start with plugging in 0, well, you start with plugging in 0. So there's actually going to be 13 total terms here because I'm going to start with 0 and go all the way to 12. So again, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 13 total terms. All right, so here we go. So again, I'm going to plug 0 in. So that would be cosine of 0. 0 times pi is 0. So what's cosine of pi? You might have to dust off that unit circle. But cosine of 0 is 1. Plus, now I'm going to plug in 1. So cosine of 1 times pi is pi. Cosine of pi is negative 1. Plus, and now I'm going to plug in 2. That'd be 2 pi. Cosine of 2 pi, back to 1. Now, if you remember anything about the unit circle, basically we're just going to be going 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So we're just alternating between 1 and negative 1 because, again, for the next term, for the third term, and sometimes it helps to label, right? 0 term, first term, second term. Now, again, I want to say this one more time. 0 term is weird. In a sequence, we don't really talk about that, but it says to start with that term, so I'm sorry I had to do it. So again, the third term would be, again, plugging in 3. So it's going to be 3 pi. And use your unit circle, cosine of 3 pi, back to negative 1. So if I just keep going, fourth term, 1. Fifth term, negative 1. Sixth term, 1. Seventh term, negative 1. Eighth term, 1. Ninth term, negative 1. And again, listen, I know it's easy to keep track. But once you see the pattern, it's pretty simple. But just use little right here, fifth term, sixth term. If this helps, feel free. Seventh term, eighth term, ninth term. And I'm almost done. I'm going to come down here and skip a line. The 10th term is going to be positive 1. The 11th term, back to negative 1. And the 12th term is going to be back to positive 1. So 9th, this is the 10th term, 11th term, and 12th term. And I'm stopping at the 12th term. Now, this is awesome because, again, if you add these together, you get 0. 0, 0, 0, 0, 0. So my final answer is just 1. Crazy, right? But again, I know there's a little bit of trick here, which makes it weird. But again, come on, we got no trig. It wasn't that long ago that we did some trig. But again, it's pretty easy because all we're doing is we're only plugging in positive whole numbers. So it actually makes it very easy to understand 0 pi, 3 pi, 4 pi, 5 pi, 6 pi. Very simple in that unit circle. All right, let's do one more example down here. All right, so now, oh, this is weird. Infinity. What? An infinite summation? That sounds like I'm going to be here forever. Okay, well, oh boy. I don't think I would ask you to do that if there wasn't something weird going on here. So let's try to figure this out. So again, I'm going to start with the first term. So I'm going to plug in 1. If I plug in 1, I get 3/10. Okay, let's keep moving on. Plus, now I'm going to plug in 2 for the second term. So that's going to be 3 over 10 squared, which is 100. Okay, now I'm going to plug in 3 for the third term. That's going to be 3 over 10 cubed, which is 1,000. Now, at this point, you probably see the pattern. So when I plug in 4 for the fourth term, I'm going to get 3 over 10,000. And I'm going to keep doing this technically forever. I mean, it literally says infinite. So it says don't ever stop, which seems kind of impossible, but not if we dive in a little bit closer. So 3/10 is 0.3, exactly 0.3. So I don't mind 0.3 because 3/10 is exactly 0.3. 3/100 is 0.03. So if I stop now and just add together the first two terms, 0.3 plus 0.03, I get 0.33. Okay, let's keep going here. The next term is 3/1000, which is 0.003, exactly 0.003. So if I add that over to here, I get 0.333. Okay. The fourth term was 3/10,000, which is 0.0003. And again, if I add that over here, I get 0.333. So I kind of see where this is going. If I just keep adding and adding and adding, since the number itself, since each individual term is actually getting smaller and smaller and smaller, 0.000003, 0.00000003, 0.00000003, and I just keep adding all those together, I just keep adding threes on, so it looks like this summation, even though it's infinity, which seems dang near impossible, but because the terms were actually converging, meaning they were getting smaller and smaller and smaller, the terms were getting closer and closer to zero, then I can actually add them all together and it makes sense that I get 1/3. 0.3 forever is 1/3. So even though there was an infinity sign there, logical thinking and thought process actually allowed me to answer that question. And this brings me to something that's actually really, really, really important, and that is the difference between converging series and diverging series. So let's actually first start with that diverging series. So a diverging series is probably what's most common. It's the sum of the sequence just keeps getting bigger and bigger and bigger. So if you keep adding more and more and more terms, so you add 12 terms and 13 terms, 14, 15, 16 terms, you're just going to keep getting bigger and bigger and bigger. So this is like all arithmetic sequences. Now, again, when I say bigger and bigger and bigger, that could be in the positive direction or the negative direction. You know, we can get -10, -20, -30, -40, -50, -60, -70. So we're getting bigger in terms of the value, but it's getting smaller because they're negative. But again, it's going forever in one direction. So a diverging series is basically that you're not going anywhere. You're going towards infinity or negative infinity, right? If you keep adding, you just keep getting bigger and bigger and bigger in either a positive or negative direction, which is what all arithmetic sequences are going to do. But converging series is the one we literally just looked at, where we can keep adding and adding and adding and adding and adding, but we actually converge onto a specific number. And that was in our previous example, that was 1/3. So even though I was adding and adding and adding and adding and adding, I was able to eventually converge onto a specific value of 1/3 because I was adding and adding and adding smaller and smaller and smaller numbers every time. So I converged onto 1/3. So this is an important topic that we understand. Is converging is your infinite summation does actually get to a specific value, whereas a diverging series is if you go towards infinity, you're just going to keep getting either bigger in a positive direction or bigger in a negative direction. You don't actually go anywhere besides infinity. So it's important that we understand that. Now, moving forward, here's where we're going to go next. Okay, summations or series are pretty fun. Adding numbers together. Who doesn't like adding numbers together? But they can take a little bit of time. I mean, the examples we've done so far didn't take forever, but imagine this example. Imagine if I asked you to do this by hand. So we have a very simple arithmetic sequence, 2k plus 6. We're going to take pretty easy. First term is 8. Second term, 10. Next term, 12. Pretty easy. But I want you to add the first term all the way to the 150th term. I mean, listen, I could do it. It's not impossible. But boy, that's just going to take me a while. Again, plugging in the first term, plug in 1. First term is 8. Plug in 2 for the second term, 10. And then you kind of get the ball rolling here and you see the pattern. But again, they want me to do that all the way to the 150th term. Now, I actually can find that 150th term really easy. 2 times 150 plus 6. The 150th term is 306. But again, I got to add all these terms together, 16, 18, 20, 22, all the way to 306. I don't want to do that. That's going to take a lot of time. Well, two things. Our calculator can do summations for us, and I'll show you that in class, but that's cheating. I don't want to recommend using that, but it's cheating because it's going to give you the answer when you don't have to do anything. Now, you may like that, but as a teacher, I don't. But thanks to Carl Gauss, an old mathematician, we could actually find summations like this really easy. But they do have to be either arithmetic or geometric, and we'll learn about those in the next few videos.